We're going to look at ionic and molecular solid properties and intermolecular forces. So in crystalline solids, particles do not slide past each other. They're going to vibrate in place in a crystal lattice. Melting takes place only when the temperature is high enough that the kinetic energy exceeds the electrostatic forces holding the particles in place. We're going to look at ionic solids, molecular solids, and macromolecules. In ionic solids, the ions are ordered in regular three-dimensional arrangement and are held together by ionic bonds. The electrostatic attraction between the positive and negative anion and cation is the ionic bond. So each sodium ion is attracted to all the surrounding chloride ions that are around it. You should be able to use Coulombic forces to explain what holds ionic particles together in the ionic bond. So here we have that force, and this should be proportional rather than equals, is proportional to the ion charges, Q1 and Q2, and D, the distance between them. So the distance between them, D, is the distance between the nuclei. So you're going to look at the very center of each ion. Coulombic forces are going to be higher for ionic compounds with highly charged ions. So magnesium oxide, you have Mg, and Q1 is equal to positive 2, and Q2 is equal to negative 2. So Q1 times Q2 has an absolute value of 4, whereas for NaCl, Q1 is equal to plus 1, Q2 is equal to negative 1, so Q1 times Q2 is only equal to 1 if we're looking at the absolute value. So magnesium oxide has the higher melting point. Coulombic forces are higher for ionic compounds with small ionic radii because the smaller this value is, the larger your force is going to be. Hence, NaCl has a higher melting point than KCl, and that is because Na plus is smaller than K plus. When you are writing these essays, make sure that you are always talking about the ions and not the atoms. For ionic compound properties, ionic compounds conduct electricity when they either are molten or in the aqueous phase. They cannot conduct electricity in the solid phase because you have no mobile charges. Once you either melt or dissolve the sodium chloride or any other ion, now the ions can move and conduct electricity. So these represent electrodes here. So we've got an electrode on this side. I didn't write that very well. And another electrode over here. Ionic compounds are brittle, which means they're also non-ductile and non-malleable, because the positive and negative ions are alternating. If we were to smack this with a hammer, let's see if I can make a hammer here. Boom, I smack it with a hammer. What happens is now I have knocked these ions so that they are directly, in some places, across from each other. So now what's happened is we've built up a repulsion here. And you're going to have cleavage take place. So these shatter very, very easily. So that was ionic solids. Now we're looking at molecular solid properties. So molecular solids, the particles are molecules and they're held together by intermolecular forces. So let's take a look at what IMFs are holding carbon dioxide together. Well, if we have CO2, and I'm not going to draw all the lone pairs, the polar bonds are canceling each other, so this is nonpolar. So that means that the only IMFs we have in this case are London dispersion forces. Whereas water, we have the intermolecular hydrogen bonding. Remember to write this out if you're writing an essay. We have dipole-dipole attractions, and we also have the London dispersion forces. So we would expect if we want to know which substance has the higher melting point, that H2O would have the higher melting point. Water has London dispersion forces, dipole-dipole attractions, and intermolecular hydrogen bonding, whereas CO2 only has the London dispersion forces. Now, remember this phrase to take it home. Water's stronger IMFs will require more energy to overcome. This next example is subtle. So, molecular solids, the melting and boiling points depend on the IMFs. The more the IMFs, intermolecular forces, can interact, the stronger the attraction. Molecules that pack tightly together can have unusually high melting points because the intermolecular forces, those electron clouds, can become in very close contact with each other. So let's take a look at a little example here. We have benzene, C6H6, compared to toluene, C7H8. Now, as predicted, toluene has the higher boiling point because it has a more polarizable electron cloud. It has more total electrons. So if we look at the melting point, we go, hey, toluene should have a higher melting point too, but it doesn't. Benzene has the higher melting point. And the reason is that benzene is a completely planar molecule. And that means that it can stack very, very efficiently. Whereas benzene has this bulky CH3 group hanging off the side, which messes things up. Let me erase this here so you can see what's going on. Okay, so the AP exam may ask you to explain or predict. They would not expect you to predict benzene's higher melting point because this is a subtlety. Let's take a look at another picture of this. This would be benzene, where we've got a planar molecule. And this would be our toluene, where this would represent that big CH3 group hanging off the side of the rest of the molecule. And it messes up being able to pack things efficiently. Hence, toluene actually has the lower melting point. Now let's take a look at macromolecules. These can be either man-made or biological molecules composed of small molecules called monomers that are then linked together by covalent bonds via polymerization. So this is the man-made macromolecule polyethylene, where we start with ethylene units, and what happens is each one of these double bonds actually becomes a single bond over to yet another ethylene monomer, and we make this big long chain. There are a variety of different types of man-made polymers. Nylon polymer that's used in carpets is a common one, and these are held together, let's see if you can recognize them, by intermolecular hydrogen bonds. So there's a bunch of intermolecular hydrogen bonds between all the various nylon fibers, and this holds them together. Proteins are a type of natural polymer. They are chains of amino acids. So here would be an amino acid chain. So that's the first level of order. Then intermolecular forces between the amino chains, so we have IMFs between the chains, can either cause the IMFs to form, the proteins to fold or to form spirals. Then there's tertiary structure, where some of the primary or secondary structure may be hydrophobic, water-hating, or hydrophilic, water-loving, so it will fold. And then finally, you can have several proteins getting together in the quaternary structure. What's really important to remember about this, and what you're likely to see on the test, is that intermolecular forces control the shape of these larger macromolecules. So for example, here is the double helix of the DNA strand, and we've got the intermolecular hydrogen bonding taking place between the strands, and that's what makes it form that nice double helix. And that is the end of this PowerPoint.